Hello, everyone. Welcome again to today's seminar. My name is Jimmy Hu, and I'm a Sharp GPC consultant. Today, I'm going to talk about one of the main I/O features in parallel programming, the MPI-IO. Well, today, because it's just within 1 hour, I'll focus on the basics. So maybe next time I can continue to talk about the advanced features of MPI-IO. So in this hour, I'll start with some basic concepts of the I/O, parallel I/O, and the common approaches in programming, as well as the file handle issues. So I/O stands for input and output, as we well know, and sometimes we may simply refer it to be read and write in a program. So it is needed in all programs, but it's often overlooked. So basically, I/O deals with two problems. One is the mapping. So that is basically how to convert internal structure and domains to files, which are stream of bytes. The other is transport. That is how to get the data efficiently from hundreds of loads on the supercomputer to physical disks. So the right side of this simple diagram illustrates the two abstracts. So from a program point of view, so we just need to write an instruction and to say write 10 words to a disk. So it's just that simple. We don't need to understand what's going on. However, from the system point of view, so we issue the write command. Well, it depends on the system infrastructure and or container, what type of things. So it will generate a buffer in the write type, and it will set a buffer size and put the data to the buffer memory, and then it will write to the disk. So there is some things on the way, and we don't care about it. And while in the I/O, the file handler normally will have a few things to deal with. So such like file open, you need to open file, or you need to do read or write. And then file view is say in a parallel situation, you need to understand which part to start. And at the end, you need to release the handler and to close the file. And in terms of the parallel I/O, and then the other big things will be the performance and the speed. So that basically will depends on the data size, and it depends on the scalability. There's many factors in that end. So yeah, we may address some, and we may not. And so we're interested in parallel I/O. So which will allow us to deal with very large data sets while running massive parallel applications on supercomputers. A good I/O is not trivial, and the challenge wrote here are the performance and the scalability and the reliability, because involved in multiple processes and also on different load, for example, on supercomputer. So it's a concurrent thing, and many issues may be involved in terms of data performance issues. And also it depends on the amount of data. And when you deal with a large data set, and it will may be a challenge. And then the latency to access to the disks, it's not a traversing at some times, and the data portabilities. So, so one cannot achieve all of the above, and then we want to do as best as we could. And the solutions to manage I/O in parallel applications So must take into account the different aspects of the approaches and the inner implications. So basically, need to decide what's the most important. So in terms of parallel I/O, say at the program level, or it need to deal with the concurrent read or write from multiple processes to a common file. And the system level, however, depends on parallel file systems and hardware that actually support such concurrent access. So here, we can actually give this sort of simple diagram to basically to list or give a rough list of the layers of I/O. So, like explained by this red diagram, and the top from the top right. So it's basically the applications. The applications is programming instructions, program operations. It's basically to issue read or write commands, right? And then in the middle level, we're involved with some, say, high-level libraries. Right now, the most popular one, HDF5 or the parallel latent CDF. And those libraries are based on the system tools for I/O, like all the computer systems, therefore POSIX, I/O. And then they mostly right now is those high-level libraries depends on MPI-IO. That's what we'll talk about that. The lower level is a parallel file system. The parallel file system depends on what type of systems you are using. For example, Lost is basically dominating in the supercomputer, and also this is our clusters file system Lost, where they have the systems enabled for to the parallel I/O. Okay. So build on that, and then now we can basically talk about the way to organize I/O. And then we have to think about it, and it should be well considered in the context of the entire application, the workflow, or not just one simple thing. It depends on the application, right? So several natural choices, certainly one is one file per program. I think this is the or dominant one right now. And then we may think about how to match the workflow, how to use some other tools to do it, or use the high-level libraries or something. Or certainly you may well take a simple approach and say one file process. And then in this case, maybe easier in programming and whatever, well, maybe whether it work for you or not, it's not matter. And you can actually to do find that I/O like one per node or something. So the following few slides, I will basically talk about each situations, the pros and the cons, and then we will have a better understanding before you go to the real programming things. So this one is actually in its first approach to manage I/O, and called it as a basic serial I/O, and it's basically is for single write. So in this case, the diagram showed so parallel application they use a bunch of processes, and then the way they do I/O is just allow one process to perform I/O. And that basically is all the processes, they need to communicate, send the data, and to the, we say master processes. And the later master processes were to deal with and read or the write. So this is basically the file view, say it's on the buffer or on the disk side. So we can certainly know, and this is easy to program. And for the beginning of the MPI programmer, we always do this, right? We say if my ID is 0, we do what. The others maybe idle at that time. It's good and for the start of the parallel programming. So this is basically you need a data aggregate and or we call it duplication. And certainly will, in lots of things, if the data is big, it takes time and for you to do it. And the first one will need maybe much bigger memory and the buffer to hold the data and to that. So the easy thing is easy to program, easy to understanding. But the problem is it's time consuming. It may not scale. And because time increases linearly with the amount of data, and also the time increase a lot with the number of processes. If you a lot of tons of processes to use, and they have additional data or read and write data, it will take a lot. And also need to take care when doing all-to-one kind of communications. And then, so this is the one type, and we'll start with this, and eventually we'll try to find a better approach. And the other one called distributed I/O. So in this case, as this diagram shows, is one file per process. So each process, right, the file to the local or whatever, wherever, right? It's quite straightforward. And yeah, and again, so the easier things, easy to program, and they don't need the communication for the data between or among the processes, and all processes perform I/O to individual files, right? And the problem is, say this will not scale at large process count as well. So the number of files create bottleneck with metadata operations because we have so many tiny files, and the simulation disk access will create contention for the file systems. And then most importantly, at the end, we want a sort of resource, you and connectivity. So afterwards, you may still have lots of work to do. So the third one will be the approach. It's called shared file. And in this case, it's each process, they have the individual writer. And then all process will write to, the system has one file, right? The file is shared among all the processes. So all processes will write to specific block of the file. And then synchronization is necessary to provide write conflict. And then this will need to cooperation between the processes and the cooperations, at the file system level. So this process will not need a communication between the processes where you don't need to send the data back and forth. And however, multiple processes may still need to compare and certain region of the file. And certainly they may have a problem to leading to log contention, or eventually they may have lower performance at some cases, and it depends on the networking thing, or depends on the file size things. However, this is basically the dominant idea, and this is the approach, and we're taking right now most of the applications, and including some high-level I/O libraries such as the parallel HDF5 and some others. The company do this type of approach. And certainly, there is some complicated management things and on the system level, and something is not necessary to worry about to the high-level programmer. Okay. And then more advancedly, and they are certainly still the shared I/O and the shared file system, file. And then this time they do connective writers. Connective writers is not each processor. They will individually to do it. It's it's a sort of do a sort of data aggregations And this declaration is not like the first one, all have to send it to one process. Doing this type of things, well, certainly you want to improve the performance. If performance is not improved, well, this will, think about, well, leave it alone, right? So this is basically where maybe some processes will film the gallery data and then do the input and the output. And certainly, and this will normally deal with the available high-level libraries, and you don't need to worry about too much about details. And then, you need certainly a sort of more complicated the file handler and take the task behind the scheme and allow a single logic view of files. So file view will be main part and in sort of I/O. And when we talk about the basic one for today. Okay. So we know this is all kinds of approaches, and now we were down to the real approach. So let's call it parallel MPI-IO. So MPI-IO was introduced in MPI II. So it's by definition, or you wanted to generally talk about what's MPI-IO. So it's a set of extensions to the MPI library that enable parallel high-performance I/O operations. So as long as you have basic knowledge about MPI, you know it's a library set of library API, and basically in your program, you call and make a calls and cooperate the process. The person will work concurrently and to make your things done instead of the CPU by a group of CPUs, right? So it provides a parallel file access interface that allows multiple processes to write and or read to the same file simultaneously. So the MPI try to address and the parallel operations in a broad way and for reading and writing. And like here's the I/O to only one file, or it can do, say, many files. And you can deal with, say, contiguous and file or non-contiguous file I/Os. And then you are individual, just like the case we talked about individual writer, or it can do connective I/Os. And then it may do asynchronous I/Os. So it has another things from easy to complicated, and gradually, and it hope to cover and provide that portable program interfaces and for mainstream of parallel programs. So the purpose will certainly be efficiently data transfer between processes, potentially good performance, or to enable high performance I/O operations on large data set, and utilize the backbone of many parallel I/O libraries such as LetCDF and the parallel HDF. So this is basically the introduction and for the concept sense. And then before we go to the real API programming level, and I think it's important to bring up a few more basic concepts about the file-related issues. So the first thing is because we're all still files, and that's the basic. So in all the MPI operations, so the first thing we'll to understand the file handle. So the file handle is a data structure which is used for accessing file. Okay, and we can define a default file handle or whatever we can define, and in the MPI environment. And then is the file point. File point is basically the position in the file, where to read or write. So file point is the key, and in the file seek and to set up offset, and for each process to access which part of the files. And it can be individual for all processes, or it can share between processes. And that basically you do individual or you do connecting. So it is accessed through file handle. So bring this up again in the seek command. And then continue and it's the file view. File view is a part of a parallel file which is visible to processes. So on the system side, so each processes and will understand the file and will know which part is what and which offset or which start point or the format and ready to work on what part. So it enables efficient non-contiguous access to files. So we're not talking about file view in detail today. I hope I'll talk about maybe next time, and we'll go to some details. And then it's called connective and independent I/O. Connective I/O is MPI, coordinates the read and write of processes. So that's the fourth situation, the diagram which I showed just now. And then it's independent, and independent is no correlation by MPI, independent I/O. And that's the third situations, and that's the basic one, and still dominating one. So that's what we want to address, and basically for today. And then the third one, in terms of the concept of the MPI-IO, this is closely related to the arguments with the contributions in operation in MPI-IO commands. So the first one is called the displacement. Displacement of a position with a file is the number of bytes from the beginning of the file. So this diagram will show that if we say where is the position here, when we say the position here, and say, well, each unit is 1 byte, and this the second one is called elementary data byte. Elementary data byte, each byte is basically in the unit of 1 byte. So it's an API data type. It could be predefined or derived, and is used to say the file view and the file access operations. So you can say that it will say, oh, display will be 12 because it will start there is 12. And then there's offset. Offset is important, and it's actually each process needed to understand the offset for him to start to read or to write. So offset is a position of file given in terms of multiples of the E byte, E types. So offset will be, it is a multiple of E types from beginning of the current view. So in this case, if it's here, well, the offset will be 12. And different and system may have to start with a different offset and to do it. So on file opener view begins at the start of the file, and then when on files, the E type is a byte. So that's the basic concepts before we go to the details. Okay, so now I think we can go to the operation side, the basic I/O, MPI operations. So what we'll provide today and the basic I/O operations, the file open, the file seek, the read and the write and the close, and then the combinations and the different situations about that. And particularly we'll address it and we'll show it later. And the open and the close files connect to operations on the same file. So they can actually include many modalities to access files, like compressible, and or then they can have a code of joint or combined and things there. So the read and the write are quite similar to, when we do MPI communications, we like the send or the receive of the data to or from above. So let's talk about is a sort of communications among them, right? So each MPI processes has its own local pointer to the file. So let's call it the individual file pointer. That's what we will talk about today. And for seek, read, and write operations. Offset variable is a particular kind of variable, and it is given in elementary unit E-type access to files. That will be defined on the seek by the seek command, and then to make sure each process will understand where to start, where to end. So that's a few steps you need to take, and I have simple examples and to show to let you understand the concept a little bit more. It is possible to know existence of each subroutines or say on the functions. Okay. Now we go to the real, and as a programmer, we're more interested in actually the real thing and the real API, and actually understand it and then how to use it. So the first thing bring up here is open file, is file open. And then the green bar that show is the syntax for the C program or C++ program. And then blue part is show the format for Fortran. Now basically they are the same, right? Just because the language itself, so you have slightly different. So what's the arguments there, or you say the contributes there? What we have are the same. The first thing is you need to find a communicator. So the communicator and in MPI, typically we just use the default and the MPI COM word and to perform the MPI and the communications of MPI-IO here as well. And certainly you need to give it a file name as a character type, right? And then is a mode. What does a mode mean? And a mode is a file access mode. And we'll bring up next page for details. It's actually defined, say, the file, the mode is, say, it could be you open the file just for read only or write only, or if for write, if no file exists, you create it with that file name, right? Or your access the file is for read and write as well. So naturally you have to define to open the file for what. And then there's an MPI info. The info is basically is a hints to implement for optimal performance. And basically want to tell it what to do and in purpose or specific things. Otherwise, and you basically use the default MPI info lar is a low hint. And then the other things, the final thing is the file handle. So that's the MPI file, and the default you can always use the default. So this is the command. So or collective calls for process in communicator. So you need to open file first before you do any read and write or do whatever on a file. That's the first step in I/O thing. So this is basically list pretty much the most used file access models, we call it a mode. So we have a number, MPI defined a number of access modes. So I suppose for MPI files, the mode argument, so it's open, defined the access mode. And for max mode can be combined. For example, in Fortran's case, so you can use addition or can use or IOR or functions. And basically, in this case, basically you want to create a new file, and this file, what does that Excel mean? Excel means generate an error if existing created file already exists, right? Or you can basically you create a file for write only. In C's syntax is basically use all to do the compilations. So create a file. If the file exists, you throw the error and then you basically to do the file write. So what I have is, as I mentioned briefly, that's read only or read write or write only or create, or this is a simple file exist. Or you can do a delete. So by the end, you delete the file when the file closes code, or you can append it, or those type of things. Okay. And then close the file when everything is done is quite simple. The syntax, well, you just close the file. And you close the file, and it also is a connective operations, the same communicator used to open the file. And the close file, and when the file access is finished, it's basically you need to free the file handle, right? So each time you have a file, the open file, you need to close it. And just like sometimes you open buffer or memory and close it and remove it. So, and then I think the first part you need to understand is the file seek command. So I need to bring up the file pointer again. And we talk about a file pointer is basically give position in a file where to read on the write. That's quite important when one file is worked by multiple processes. So it can be individual for a process or share between the process. So each process moves its local file point and with it, so individual file point. So this is basically, and the result is give an offset for each processes to work with. And the command and argument is file handle, the same file handle data structure, which is used for accessing the file. And then it gives a displacement in bytes. So displacement that we talk about, or it count from the beginning and of the file, how many bytes and it's been there. And then where it will give, from here, it will give an offset process. And then the ones is basically the options to use. And normally people just use sig set. This basically is the point is set to offset. Certainly we have other and so like CUR, and basically point is set to the current point position last offset, or the end basically point is set to the end of the file last offset. So this is just a few options there. Okay. And then this is basically, and we want to understand to use is the read file at the individual files, the read command, the MPI file read. So the argument here is the file handle, and then it's a buffer. It's a buffer because you need a buffer in the memory to be able to hold, to read the data. And then the count, the size, and the size of your data, right? And this has something to do with the data type, with the buffers, right? And then it's data type. Your data type is integer or is a character or whatever, right? And then it's a status. Status basically is MPI. It's similar as other general MPI receive and count, all those type of things. And it's MPI status to show at lambda and those type of things. So this is basically need to keep updated position file point of reading. And this is not thread safe. And well, this is basically we use default offset defined by the sig command. So we'll talk about a little bit of thread safe thing later. So now, because we introduced that read command and then a few other things, and so this will give us a simple and I think it's quite understandable for the parallel I/O concepts. So assuming we have a file, and then in this case, and then we have a rank and how many CPUs to use, how many processors we use for, and each will have the number of processors will be, the rank will be from 0 to 3. And in this case, well, we have needed some sort of way to write and MPI to write the file size. And if we know the file size, and then we know the number of processes defined by the number of processes, we'll know the buffer size. And basically, each process, the size of each process need to access to. And then after that, we need to set up where to start. And for example, first one will start from 0 at some point, and the next one will continue. And then each will access part of the data. So that makes it parallel, right? So this is a simple example in C, and you can see well the common cores in all the MPI will start and the rank and the size. And then we define the default and the file handler and the status. And then this is the command for the file open. So we use the default word communicator. And then this will define the files. So the location of and the name of the file. And in this case, for example, the mode is defined, so MPI mode read only, and then we use the default, there's no hints to it, and it's file handling, and that's it. And then we offset and define file size, and we can actually, there's a comment we didn't bring up, and we'll be on to maybe next time, and there's a comment MPI file get size. So get size will know the file size. And in the file size, you can define the buffer size. The file size divided by number of processors. We'll know the buffer size. So once we know the buffer size, each buffer size, well, if it's integer, for example, we know the count. So how many integers inside. And in that case, we defined the buffer size, so give it enough memory for the buffer size, right? So once we have this, and then we can call file seek that command. So what is it? File handler where it start the buffer size is rank and times the buffer size. And we set this set to be offset. So what does it mean? Say if rank is 0, well, it will start and offset will start with 0. And if it's 1, well, it will start with the first buffer size. And this 2 will start here. So after 2 buffer size, right? And then after that, you can do the file read. So file read, we know the buffer size. We have a buffer defined there. We know the count. So how many integers, for example, here, and we know type is integer or status. And then this will make sure this read is in parallel, right, on each read part of it. So the offset is defined. So this, you can see the file seek command is quite important, play a role here. And we close the file, and that's it, right? And then, I think I can, on this point, and I can move it faster. And then file writer, similar to the reading, and they practically take similar and arguments. So, and when you write, when you're doing the reading, you have the read-only operations. When you're writing, or you can also do write-only, or if no file exists, you can create it. And the syntax and in file write, so you have the handle, the buffer, the count, dataset, status, right? The same thing, or this thing you update it each time we have to do it, and it's not safe. And then we can bring up this and simple examples. So this time and in Fortran, for example. And then this basically this code will do multiple processes, right? To a parallel file, and the test is defined here. The first process, when you define a bunch of things, and then here is the count, the buffer size each depends on my ID, will generate or integers or whatever here. Some and will write some integers to the file. So in this case, it's the same thing we will generate for each, depends each process will generate it. And the core file, so it's on the test, or is write only if it's not well, and create the file. And it is a default. And it is called file size, we have given it before. And then when you have file size, and then you can count. So the displacement, as I said, depends on your ID. You can calculate. You can count and the integer size. And then that means the first one will start from the beginning, and the next one will after the first has finished. So this is called by the core MPI seek is file. You have that displacement, and by default you set the default to get offset. And once you get offset, and again you write to the file, the buffer, the count, and or in this case MPI integer or status, and you close the file. You do it, right? So it's quite similar and that. So what we just talk about was using the file seek. That code is called default set of default offset. They have other better way to do it, and here we continue, and it's actually called explicit offset. CMPI they can do explicit offset, and most of the time will do better than that. And it's basically combine the seek and the read command together. So then the location to read or write can be determined. So explicitly with this one command. So this is called MPI file read add. So this was done is a handle, and then added in is the displacement, and then buffer count data type and the status. And then display size we talked about is a byte from the beginning of the files. So this will make sure is thread safe because data just now you have to count it and to calculate it. So it's not it's not thread safe. So anyway, this is not the point we're concerned about right now. So the file point is neither refresh or incremented. So and we have this, and certainly we have write the same thing as well, and use the explicit offset. So in this case, and the same thing, and then in this case, we basically combine file write and the file seek together to be a file write add, and the displacement add in, and we can do that. So we have this, and then we have the same code, and come back to review the same code. We don't need to change much. And it's actually, it's just simply copy this code, and you can run it, it actually works. And then what is simply to do this is basically simply to remove that file-seek command, that line. And this nothing changed in this right to simple demo examples. You have everything there, and it's not changed. And basically here, instead of the file seek and file write, you file write add, and you have these disciplines already characterized here. This will work exactly the same as we showed just now. And we have this, and then certainly we can do read. It's the same thing. So the first is the same examples. For the first example, the part is the same as the just now. We just need to change the following part and from the previous slides and change it to be read. So when you have read it, and then you can read it or you pass. So this is the main point for today. Is basically talk about the default offset, and then now we talk about that explicit offset. We need to show you this. Okay, and then it's not just that, and for that, open. So is that MPI-IO tried to have much more than that. So that's the basic operations, and the basic operations may be okay for majority of the applications. And then, as we talk about, it actually has connective operations. So the connective operations that can be performed connectively by all processes in communicate. So the command will be the API is actually called file read or write or. So that's because it's still connected. So all processes will do things. And then you have the read add or and write add or. So they still called connecting. So we talked today is basically for those commands, they are called individual operations, the write or the file operations. And we have connected one, and we have another talk about it today. And we'll may find time to talk about it maybe next time. So it's basically it's all process in communicator that opened file must call function, and the performance potentially better than the individual functions. However, they need more knowledge, and so that's why programmer we were more likely to call for the available high performance libraries because those are well done and more reliable. Instead, well, you have to try your own if you are not so comfortable. So if each process read a long contiguous segment in total, the rate is contiguous. So this is basically, and yeah, we'll bring this maybe in future. The other thing I want to bring up and is what we so far we talk about or called is belong to the category of blocking I/O. We put it that way, okay? And because we talk about so far, and like you do the MPI letter and send receive communication, you have a block communication or long block communication. The same thing will work for I/O, do the parallel I/O. You can do that long block in I/O. And in terms of long block I/O, it also has two two groups. So one is basically for dual independent and long block I/O. That's what we showed most of the part today. So this is just like a long block and communications, and the same parameters as in block I/O functions, right? So instead of command file reading, well, you have the file I read, write, you have the file I write, and you have I write add and I read add. And additionally, I actually bring up and I read shared. So we'll not talk about it. And then the connective command there also has operations and APIs and syntax to do long block I/O. So that we don't have time to address that as well. But that's something, and hope we can talk about in future. Okay. So as a summary for today, here I listed include some routines and say interfaces for C, and we addressed most of them. I think, oh no, not most of them, and the basic one for them, and then for the all certainly the connective one we have not touched at all. And then we didn't actually show the details for the view, and so I think view we did this a little bit more time to actually explain it clearly. So I hope I say I could be able to do advanced features about MPI in the future, and I will address that. And the same thing, we have MPI interface on the routines for both languages. That's for C, and you certainly for Fortran. The same has as long as they has a syntax for C, they have the same for Fortran. And also our simple examples I demo that as well. Okay. So, and these are the main references I used, and you can find it online as well. And some of the slides, particular diagrams, are taken from different online resources. And if you are interested, you can go to read your own. Maybe you can learn some more deeper about MPI-IO. I think that's for today.